welcome back. And now I'll continue where I left off, talking to you about using LightSIDE. So now I'm going to talk about the development and evaluation process that we advocate. It's really important to avoid overfitting. Well, what does that mean really? Overfitting is when a model that's trained is too particular to the data that it was trained on to an extent that reduces the performance of that model on data that you really care about, which is the data that you haven't seen so far. And there are ways that you can structure your development process to avoid this as much as possible. So one thing that you want to be able to do is set aside some data that you can look very closely at so that there's separate data that you avoid looking closely at. And if you avoid looking closely at data, that means that the decisions that you make about how you set up models to run experiments on that data aren't made with insight into the particulars of that data, and therefore are based on insights that must generalize from one set to another, because you got the insight from looking at one set and you applied it someplace else. So the data set that you'll look closely at in the process that we advocate, we're going to call the development set. And the evaluation set, the set that you run your experiments on, we're going to call the cross-validation set. Now, when I teach this to my students, I ask them to separate their data into three sets: the development set, the cross-validation set, and the final test set. And the reason why I ask them to set aside a final test set that I say you should lock it in a closet and never look at it until the night before you turn your project in at the end of the semester is because then what they can do is check to see the extent to which they have been successful in avoiding overfitting. So what they'll do is look closely at the development set. They'll run experiments on their cross-validation set. They'll look closely again at the dev set. They'll make changes to their configuration and run another experiment. And from experiment to experiment, they'll look to see how their performance is improving, but without ever looking closely at the details of the cross-validation set. At the end, then what they'll do is train a model using the data from that cross-validation set, and that model they'll apply to the final test set that not only did they never look at closely, but they also never ran any of the experiments up until then. And that will be the true test of generality. So here you can see a representation of the data set, the rectangle. And you can see that a segment of it has been sliced off of the left-hand side, and we're going to call that the development data. And the biggest chunk of data we're going to call the cross-validation data. And then a small segment at the end on the right-hand side is the final test data. So when I teach students in my machine learning class to use this development process, I ask them to have at least 1,000 separate data points, so 1,000 rows in their CSV file. And I ask them to place 20% of those, or 200 rows, in the development set, 70%, or 700 of those rows, in the cross-validation set, and 100 of those rows, or 10%, in the final test set. But these numbers are not set in stone. And the main point is when you run experiments, you need to be able to train on enough data to get a good model that's not... another source of overfitting is when you train on too little data. So you want a model that's trained on enough data not to overfit. Now, at this point, people always ask me, well, how much data is that? And there isn't any one answer that's always true. So what you can do is this. Let's say you have your 1,000 instances. Now you've divided it, as I've said, on this slide. Now if you take that 70% that's your cross-validation set, and now divide it so that 10% of that you're going to use as a temporary test set, and 60% of it you're going to play around with. Now, what I'd like you to do is within that 60%, randomly select 100 instances, train a model, test on the 100 you set aside. Now, select 100 more randomly. Now you've got 200, train on that, test on the final 10%. And continuing doing that with larger and larger subsets of your cross-validation set, each time testing on the same small segment. And what you should see is that performance increases as you increase the amount of data that you train on. And this is because the more data you train on, the less you're overfitting. But eventually what happens is the performance levels off. And at the point where it levels off, that's where you know that you've trained on enough data. Now, if you never get to a place where you see the performance starting to level off, where it doesn't increase very much the more data you add, then you probably could still improve your performance with more data. And so you should do that experiment to see if you have enough data in your cross-validation set, and at least be aware that you don't, and you should, if you can get more data, then that would be the ideal. And if you read the textbook, that book on machine learning that I pointed to in the last lecture, what you'll note is that there are approaches called semi-supervised learning approaches that can use data that's not labeled, but it's at least similar, and some kind of technique like that could help you to address these overfitting issues if you can't get more training data. So there's a lot more that could be said there. We'll move on for now. The important takeaway here is that you want to divide your data into these three sets: the development data, the cross-validation data, and the final test data. And then you're going to engage in an iterative process that we started talking about already in the last lecture. So first you'll see a bubble at the top left that says that you should do qualitative analysis on your development set. That's where you do what I led you through on the question versus statement data set, where you look at the data and you look at data that's in one category and data that's in another category, and you think to yourself, what's different that I want to capture in the features that I extract? Because then I'm going to build feature extractors, or I'm going to select options from the extract features panel that will allow me to get at those aspects of the text. So then once you have decided what kind of features you want to start with, then using the extract features panel, you'll extract the features from your data. And then you are going to use a cross-validation methodology to evaluate training a model with those features over that cross-validation set. And we stepped through a cross-validation evaluation in the last lecture. Then you're going to look at what level of performance. So how many errors did you get? And usually the first time you do this, you're not going to be happy with the result. So what you're going to do is an error analysis. So you're going to train a model on the data in their cross-validation set as the training data, and then you're going to use as the test data your development set. And then you can look at your development set. What did the model that you trained predict about each instance? And you can see where the errors are happening, and I'm going to lead you through that error analysis process so that you can see how to do that kind of troubleshooting. And then you're going to, based on what you find, come up with ideas of new features that you might extract. So then you'll extract those features and run another cross-validation experiment and see, am I satisfied now? If not, then you're going to do this loop again. And you'll continue to loop, doing cross-validation experiments, not being happy, then doing an error analysis, coming up with more ideas, running another cross-validation. You keep looping around through this loop until you finally feel like you have the configuration that you want. And then what you're going to do is train a model using your cross-validation set and the final configuration and apply it to the final test set to see what the result is. So an important takeaway here is that when we divided the data into three segments, the three segments you use for very different purposes. The only part that you look closely at is the development data. And you use this before you ever ran any machine learning experiments to get a sense of your data. And then between experiments, you do an error analysis to get ideas for designing new features. And all of this important design work is all done with reference to your development data. So you never look closely at your cross-validation data or the final test data. The cross-validation data is always used just for experimental purposes. Largely, you'll run cross-validations using a configuration and what does that mean? It means the set of features you extracted, the algorithm that you picked to train with, any other parameters that you set, and you do a cross-validation to estimate how good of a configuration that is. And between experiments, then you can compare the results to see, am I making progress? Am I getting better performance? Etc., etc. Now, don't be confused between feature extraction and feature selection. You always do feature extraction on the feature extraction panel, and you'll extract features over your whole data set so that you have the same columns in the data table that you're producing for all of your sets of data. However, there's a separate something called feature selection. We talked about it briefly when we were doing the walkthrough of the experiment. And feature selection is where you use an algorithm to narrow down to the subset of features that look most promising. And that's with reference to what it is that you're trying to predict. You always only do this over your training data. You never look at your testing data when you're doing this. And it's very important to be careful about that. So between the first two bullet points on this list that refer to data handling in your development process, and this last one that's about data handling in using techniques to build a model, you are always seeking to avoid overfitting by never looking at what you're testing on and even not getting a very close look at what it is that you're running your experiments on, which includes what you train and test on for the experiments that you're going to run. Okay, so now let's dig more into feature extraction. There are different kinds of features that you can use, and we're going to start out looking at the very basic features that we have to play around with, and later we're going to get into more advanced ones. So we're going to start with something that I already referred to briefly earlier, which is the Unigram feature space. It's also called bag of words. And the idea is this. You have a set of texts that are in your data set. So here, let's assume we have two texts. Cows make cheese and hamsters eat seeds. And what we're going to do is extract each word we've seen in our data set. So we have a feature for each one. Now that we have a feature for each one, when we extract features from these texts, what we do is we step through each of the features in our feature space, each one asking a question of our text. So the cheese feature asks, does this text include cheese? If it does, you put a 1. If it doesn't, as in hamsters eat seeds, you put a 0. Cows. Does it have cows? Yes, we put a 1. Hamsters eat seeds. Does it have cows? No, so we put a 0. So you can see that we step through each feature asking a question. For every feature, we say true or false or 1 or 0. It's the same. And we do it with reference to the text. So what we do is we lose the notion of order and how many times does a word occur or structure in the text. Lots of information is lost, but for some kinds of distinctions, the information that's preserved might be important. You can see here, for example, you won't be able to distinguish between cheese makes cows and cows make cheese because you lose the order information. And there are other things we lose as well. So let's just keep that in mind. Okay, so here we are back on the Extract Features panel. And you can see it's configured to use the basic feature extractor. And that basic feature extractor has a number of options, one of which is Unigrams. And Unigrams is, as I said, the same as the bag of words feature space. Now I'm going to step through the other parts of the basic feature extractor. And I'm going to use as an example the Obama healthcare bill. Now, this might not be such a great example for people who are thinking about our different language versions of LightSIDE, because that might mean that you're less familiar with American politics. But in any case, we're using a data set as an example that came from an organization in the United States called Gallup that conducts opinion polls. So in this data set, every instance was one person's entry in this opinion poll. And for each entry, we had the gender of the person, what state in the country they were from, how old they were, whether they were in favor of the bill or not, and what they said about it in a short text. So in our first example, we have a male from Virginia, age 30, who didn't like the Obama health care bill, and he said, "I think it'll increase costs for everyone." A female from Illinois of an unknown age, she must have left it out, was in favor of the bill and said, "Because the cost of health care is just out of sight crazy." And a male from Michigan, age 70, was positive about it, he just said the cost. Now, the interesting thing about this data set is the way that males and females on average talked about cost was different, and that was kind of an interesting thing. What we're going to focus on in this part of my lecture, though, is not really that aspect of this data set, but more what kind of features would we extract from the texts. Now, I mentioned that there's age, gender, and state as additional columns. So in our original data set we looked at in the simple walkthrough, there were only two columns. There was the text and then there was the category. But here we have some other features as well. And we want to make sure in the text fields section of the extract features panel that those are not checked off, but the text column is what's checked off. If you want to include those as features, you can use the column feature extractor. And that's what you see circled in red over here. But we're going to talk about the basic features. So here's an example, because the cost of healthcare is just out of sight crazy. What are the features we would extract with the Unigram feature extractor? We're going to extract every word in this text. I'm not going to underline each one. Eventually I get lazy. But you can see, it's just single words, each one a feature. Bigrams, on the other hand, are looking for pairs of words that occur next to each other in the text. So we'll have because the costs, cost of, and then of healthcare. Healthcare is just out of sight crazy. All those are bigrams. Trigrams are similar, but they're triples of three words next to each other. So because the cost of healthcare is just out of sight crazy. Part of speech bigrams are similar to bigrams, except instead of the words, it's going to extract pairs of part of speech tags. So you can see here the cost of healthcare. Each word is labeled with a tag. These tags refer to grammatical categories like determiner, noun, preposition. So regardless of what language you're working with, the segments that are of about the size of a word will have been assigned to tags. And if you're not using English, the tags also might be slightly different, but they'll have a large overlap because we're consistently using the part of speech taggers from the Stanford NLP toolkit. So so you can look up what the tag set is on the Stanford NLP toolkit website, which you can find on the internet. And for now, though, I'm looking specifically here at tags that we have in the English tagger. So part of speech bigram, just like a regular bigram, it's from two words next to each other, but it's their part of speech tag. So we'll have determiner noun, noun preposition, preposition noun, etc. So, and here's a list of the names of tags that are part of the English tag set. Now, in addition to part of speech bigrams, you can also find word part of speech tags. One part of speech by itself is not very telling. But when you look at words that are paired with their part of speech, you get to know a little bit about the sense of that word. So cost as a noun or cost as a verb are two different words, but they look exactly the same. So in a unigram space, they'll be the same feature, but if you have word part of speech pairs, they wouldn't be the same feature. Line length is a number. It's not that useful unless you want to know how much text was in each one of the instances. So in this particular case, the cost of healthcare, it would go and count the words, and the value for the feature would be 4 because there were 4 of them. At this point, I'd like to talk a little bit about what is a stop word. It comes from the search industry. They were the ones that invented that term first. And a stop word is a contentless function word, the, of, even it, things like that. Words that don't have a lot of substantive meaning, but they're important functionally in a text. Now, sometimes you might want to know, were there any thematic words or contentful words in a text? If you want that binary flag in your feature space, you would put a check mark in contains non-stop words. And here we have 2 words that are not stop words, and so the value for that feature would be yes. Count occurrences by default is unchecked. Now, okay, there are 2 different versions of LightSIDE. One of them that says count occurrences here, and the other one that says binary n-grams. You probably have the version actually that says binary n-grams. That's checked by default, which means default is a unigram feature's value is true or false, 1 or 0. If you check off count occurrences or uncheck binary n-grams, what will happen is that instead, the value of the feature will be how many times does that word occur. So you can say the cost is too great, the cost is immense, and the value of the cost feature, if you check off count occurrences, would be 2. Whereas if you don't, it'll be true because it occurred, and you won't know that it occurred twice. And when I say you won't know, what I mean is the feature space won't represent that information. Include punctuation, that's whether or not punctuation marks get counted as features. So here we have a period and an exclamation point. If you uncheck include punctuation, those would just be stripped off and not paid attention to. Sometimes you might want to remove the stop words from the feature space and only keep the thematic words. If you click on remove stop words, that will happen. And stem n-grams means that what you want is to remove the endings or beginnings of words in English, that is, that indicate number and tense and gender sometimes. So these inflectional suffixes and prefixes, as they're encoded in English, might appear differently in Arabic and in Chinese, but whatever would be the equivalent of removing those distinctions, so you get down to roots that are just about the meaning of a term, that's what you would strip down to. There's an order in which these things are applied to the text in order to extract the features in the most reasonable way. So part of speech tagging is done before any of the extraction takes place, so and before stemming takes place, or even before stop word removal. So part of speech bigrams aren't affected very much by stop word removal. The part of speech tags for the stop words will still be included. But if a part of speech engram, or actually no, I guess for the part of speech ones, we leave them in. For word engrams, though, if an engram has only stop words and you have stop word removal, you'll remove those, but you'll keep ones that have at least one contentful word. And this is, I believe, discussed in the user's manual as well. Now, when you decide what features you want, you should think a little bit like a computer. And what do I mean by that? Well, in order to increase your performance, oftentimes the features you'll use are proxies. They stand in for something. They're associated with some quality of the text. They might not be exactly the thing that you're trying to predict, but they're related to it, and so they're a good clue. It's kind of like you might not see the hamburger that somebody ate, but you might see the wrapper for that hamburger. So you can predict that there was a hamburger because you see the wrapper. The wrapper isn't the hamburger. You could have a wrapper there even if there wasn't a hamburger there because somebody might have brought the wrapper with them from someplace else. But if you see a wrapper for a hamburger, it's a good clue that there was a hamburger there. And so similarly, machine learning algorithms, they just learn things like if I see a wrapper, there was probably a hamburger. They're going to be wrong sometimes, but if it turns out that there is an association and it happens fairly reliably, then the machine learning algorithms will learn to depend on that. And so you can be proactive in providing opportunities for the machine learning algorithm to do that. And if you think about what are ways that these features might be associated with what I want to predict, that can give you ideas for kinds of features that you might want to include. And we talked through some of that when we were talking about questions versus statements. Now, I'm going to get into something that's extremely important, which is error analysis. I want to talk you through how you troubleshoot the model that you're building, because you can start in a reasonable place with some insight into your data, but it's almost never the case that the first experiment you run already gets the level of performance that you want. Okay, so I'm going to talk to you about an idea that I had for formalizing this process. You won't find it in any book, but it's what I teach in my class, and I believe it helps people to think purposefully about the error analysis process. So let's start with the idea of a confusion matrix. We already talked about this when we ran through a simple experiment in LightSIDE. So the columns, so let's say there are two categories, A and B. The columns represent what a classifier decided about an instance. So all of the instances classified as A are in the column A, and all of the instances classified as B are in the column B. But the rows are what represent what was hand labeled on the instances. Now, the rows are in the same order as the columns. So the first row is the A row and the second row is the B row. So this upper left-hand number is those instances that were hand labeled as A and the classifier classified them as A. So these were correctly classified. But the 25 were hand labeled as A, but they were classified as B. So they were incorrectly classified. This 149 are instances that are actually B, so they were hand labeled as B and they were classified as B, so they were correctly classified. But these 10 were hand labeled as B but classified as A, so they were incorrectly classified. We call these downward diagonal cells the correct classification cells, and all of the other cells we refer to as off diagonal or error cells. And what we want to do when we're doing an error analysis is figure out why these 25 instances looked different from the other 44 that were correctly classified of A's, or why did this 25 look like the 149 that were correctly classified as B's even though they're not A's. Similarly for the 10, why did they look like A's when they were actually B's? Why did they look different from B's when they were actually B's? So we call the comparison within a column the why did it look similar to something question as the vertical comparison, because we're comparing instances in an off-diagonal cell. with the correctly classified instances in the same column. So we're looking vertically. And then the other comparison, the why did it look different comparison, we called the horizontal comparison. We're comparing these off-diagonal instances with the instances in the same row that were correctly classified. Now, we want to, when we make our comparison, to do it feature by feature. We're going to look for those features that are responsible for making the 25 look different from what they are in the horizontal comparison, or similar to what they are not in the vertical comparison. So when we do a horizontal comparison, feature by feature, we're going to look to see which features are in very different distribution between the set of instances in the 44 and the set of instances in the 25. So we're going to take the average value in this in the feature for the instances in the AA column and the average value for the same feature in the 25. We're going to subtract, and then we're going to take the absolute value of that difference. We're going to call that the horizontal absolute, or horizontal absolute difference, or the absolute horizontal difference. And that's the distance between the distribution of that feature in the 44 and in the 25. And features that have a big horizontal absolute difference are potentially features that are confusing our model. In the vertical comparison, we're looking for the features that make the 25 look similar to the 149. So we're going to do a similar thing. For each feature, we're going to take its average value in the 25 and its average value in the 149. We're going to subtract and take the absolute value, and we're going to look at the distance. And if it's small, then we say that feature is in similar distribution between the 25 and the 149. So potentially that's a feature that's making the 25 look like the 149. And so then that feature might be confusing the model. So a feature could be confusing the model because it makes an instance look different from what it is. And we find that using the horizontal comparison, or a feature might be confusing the model because it makes the instance look similar to what it is not. And we call that the vertical absolute difference, or the vertical comparison. Vertical, horizontal. Okay, so how do we do this error analysis? The first thing is, so we were looking at the sentiment sentences data set in our simple walkthrough, and now we're going to do that again, but now we will have divided that into two subsets, a development set and a cross-validation set, and you see that here. We are going to load the cross-validation set on the extract features panel. We're going to extract a Unigram feature space. And then on the build models panel, we're going to load the development set and run an experiment. And then we're going to do the error analysis on the explore results panel. And you can see on the explore results panel, we have our confusion matrix here. And we've selected an error cell and we're trying to explain the errors in that cell. And so we're going to look at some numbers that were computed over here. We can decide which columns we include there by clicking on them here. And we want to include frequency so we know how often a feature in the error cell was non-zero, because we want to find features that happen frequently, because we want an error that's causing problems very frequently when we're going to spend effort to try to fix that problem. Because if it doesn't occur very often and we fix it, it's not going to make that much of a difference overall. So we want to know about the frequency. Here we put in the horizontal absolute difference. So we're going to start with the horizontal comparison. That's comparing these 38 instances with the 471 that are correctly classified in the same row. And then we're going to look at the feature weight. So we trained with a weight-based classifier so that we could look at to what extent is the model paying attention to each feature. Because if the model is already more or less ignoring a feature, regardless of its distribution, it's not really causing trouble. So we can use this to identify features that are worth spending some time on. And we identify that maybe movie is a good one to start with. It doesn't occur a huge number of times, so in hindsight, maybe it wasn't a great starting place. But it does have, at least in this ranked list, a not tiny horizontal absolute difference, and the weight is somewhat substantial. So movie could be a confusing feature. So then we're going to move down to the bottom part of our Explore results panel. And we're going to say filter documents by selected feature. First you want to pull down document display in this pull down menu and click on filter documents by selected feature and documents from selected cell only. So you can see here are the examples, the 5 examples in the error cell. So out of 38 examples, 5 of them had the word movie, and they're all listed here. And then if you click, you can see the actual text over to the right, and it highlights for you the word movie so you can see it in context. And so this gives you a sense of, well, why is it that, so if I'm predicting positive and I see the word movie, there's a negative weight associated with it. Why would there be a negative weight? It must be because usually when people say movie, they're complaining. Right? Okay, well, that's true. But sometimes, apparently, they're not complaining when they say that, because the ones in this cell where they mentioned movie, it was actually positive. So what's happening is that the model is noticing that usually you don't explicitly refer to the movie in these sentences unless you're complaining about it. The sentiment sentences are extracted from movie reviews. So then it starts to associate the word movie with something negative, but in fact, movie itself isn't negative. And so, what can we do about that? In this case, what do we see? So here we have, it's actually predicted positive when it's negative. So here, this is the opposite problem. That would have been the problem with these 38 because it was predicted negative when it was positive. But here, actually, it is negative and it's predicted positive. And in that case, the problem here is it's negative and its weight is negative, which is the right thing to do. But there are other things in this text that the model is ignoring. I think what's happening is so much weight is put on negative, but other words are counteracting that. And so then it's missing the fact that there are other words. And I think that actually in this sentence what's going on is that it's got isn't scary, isn't funny, but because it's just doing unigrams, it's seeing funny, it's seeing scary, and usually when people talk about that, that's a good thing. We see surprise, and if we just saw the words that were around, so we see not scary, we see not funny, and no surprise, we would have known it was negative. And so it's depending upon movie, but actually that gets us looking at this example, but that's drawing weight away from some places that should have given it information. And the reason why those places are ambiguous, they're not drawing as much attention as they should, is because it's not seeing the words in context. So what we end up deciding, and you would see it more if you look through all of these examples, is that the unigrams are making these words very ambiguous. And so the words that should tell us something aren't telling us as much as they could, because some words like surprise and scary and funny are less good predictors if you ignore that sometimes they're next to no or not. So we can fix that if we include also bigrams, because then we would see what word each word is next to. So now we're going to try to fix the problem by re-extracting our feature space. So we're back on the Extract Features panel, and you'll see here we're keeping unigrams, but we're adding in bigrams, which we think will be more telling. And now we're running our cross-validation experiment again. First, we run Unigrams and we see its accuracy and kappa, and then Unigrams and Bigrams, and we see its accuracy and kappa. And we can compare these two experiments if we go to the Compare Models panel, and we see that the model with Unigrams is a little bit less good than the model with Bigrams. And we can see there's a t-test down here that says that the difference is marginal. It's not significant, but it's marginal. Now, there's another way that we could get even more context around the words in our text, and that's with a feature extractor called Stretchy Patterns. And you can learn about Stretchy Patterns in the user's manual, and we can tell LightSIDE to go ahead and use Stretchy Patterns by clicking on it. And then if you scroll down on the right-hand side, underneath the configuration for the basic feature extractor, we have the configuration for Stretchy Patterns. And there are a lot of aspects of Stretchy Patterns. I'll just point to a few. So here on pattern length, we're telling it each one of these rules that we're going to extract, how many elements can be part of those rules. We have here, it can be between 2 and 4 elements long. And in those rules, we can have some wildcard symbols that can stretch over words and more or less ignore what's in those words, and we can determine how long those can be. And this slider says those gaps are between 1 and 2 words long. We're saying here we want to include words in our features, and we can also create categories. The categories are in a folder called Categories that you'll find inside of the plugins folder from the zip file that you got when you unzipped LightSIDE. And you'll see that there are some built-in categories, and you can create your own. Each one of them is just a text file. You can look at how they're structured. What you have in the text file, it's named after the category. The first, it's a list of words inside of the file. The first word is the name of the category, and then each row after that has one word that's an element in the list. So for example, the negation or negative file has in its first element strong neg, that's the name of the category, and then there's a whole list of negative words that are underneath of that, and you can see that. So you can click on add next to categories and select a category to include, and then if you want to say to the extractor, you should include at least one of the categories from my list in every pattern you extract, you can click on that, and you get to decide things like, do you want to include part of speech tags too, etc., etc. And you can read about all of this in the user's manual. So right now we're just going to put strong neg, so ways of being negative like not or no, and other negative words, and we're going to force that all of our categories are going to include something like that. And now when we extract, you can see how it's creating some of these template patterns down here. So like this one says, if I see apostrophe S, the word just, any word, and then one of the words from my strong neg list, I'm going to say that this pattern occurred at least once in the text. And that's how these patterns are used, and they're able to give more context than just a bigram does. But because they can generalize a bit, you've got these categories, you've got these gaps, then they can occur more times and more flexibly than a bigram or any other kind of n-gram that requires that exactly the words that are listed in that n-gram appear exactly that way. And now if we run it, we do even a little bit better. And we can see if we compare the model that included the stretchy patterns with the baseline, we have a significant improvement. And in both cases, what we were trying to do with the change to the feature space was to get more visibility around words so that we didn't have the confusions that we talked about having seen. Because we believed that the problem, the reason why movie came out as a confusing feature, wasn't so much about the word movie itself, but because the things around it that should have gotten more weight didn't get that weight, because they were ambiguous, and we wanted to make them less ambiguous by being able to see them in context. And we made a little bit of headway by just adding in bigrams, but we had more headway by adding a more powerful, expressive kind of feature like stretchy patterns. So if you look in the slides that I'm going to pass on to you, you'll see, some thinking along the lines of what I talked about, how you can strategize. So the most important thing to notice here is that when you're doing your error analysis, you'll pick an error cell, you'll pick a feature that you think might be problematic, and most importantly, even though here you see some frequencies that somebody was looking at in this example, this came from a student's assignment where they were doing an error analysis. The most important thing is that they went back into the text to see how the problematic feature appeared and tried to think, what would be a more expressive kind of feature that would help these instances be handled more appropriately, that would draw attention to those aspects of the text that signify positive versus negative in this case. In your particular case, you'll be trying to go for different categories, but you'll have some insight into what is it that makes texts fit that category from the qualitative analysis that you had done. Here, a different kind of feature, not stretchy patterns, but regular expressions were used. And if you know some programming, you know how to come up with patterns using regular expressions. It's worth learning a little bit about regular expressions if you want to be able to do this kind of a thing. So I'm going to close there for this demonstration of error analysis, and I encourage you to go and practice these skills.